Hello, engineers. What I want to do today is a couple of practice problems here to maybe clarify some things from the notes and make sure that we're all in good shape to be able to do these problems. They're a little difficult, but they're not that tough if you kind of follow through and use all of the tools that you have at your disposal. All right, so let's start with this one. It says a 2x6, actual dimensions 5.5 by 1.5 inches. This is something I didn't really get into when I was doing the video, but when I say a 2x4 or a 2x6, those are dimensional lumber, like you would get at Menards or from a lumber yard or things like that. And it's hilarious, but the dimensions 2x4 aren't actually 2 inches by 4 inches. That's what they're cut before they are dried, and so they get smaller as you take out water, and they end up at 1.5 by 3.5, or for a 2x6, 5.5 by 1.5. So that's what I mean. You don't really need to know it. It's just I'll always put the actual dimensions in there for you. So okay. So there's our dimensions. It is 14 feet long, so that's our length. But remember, length has to be in inches, so we're going to multiply this by 12. It has a modulus of elasticity of 5,400,000 psi. It is loaded in the joist position at the center with 550 pounds. How much will it be deflected? That just means how much will it bend? Okay, so when we're asking about deflection, all right, that's this delta max equation that we have right here. Okay, so what I'm going to do is I'm going to write all of those variables over here. E equals I equals. These are all of our numbers that will come from the problem, okay? This right here is our E. This right here is our F, and then our L is times 12. This is where we get our I, but it's not an I right now. So let's start by filling in what we have. Delta max is what we're trying to solve for, so we're just going to call that delta max. F is 550 pounds. Okay, length, well, it's 14 feet times 12, because there are 12 inches for every 1 foot, right? So 14 feet. So that's 144 plus 24 is 168. That'll be 168 inches. You can do the math if you want to, or you could trust me. And then we've got E, which is the modulus of elasticity. That's how much it's going to bend. That's 5,400,000 psi. And then I. Well, we're not given I right here. We're given 5.5 by 1.5. We're given the dimensions. And we have this other equation up here that allows us to find I. So I'm just going to put that in there, BH to the third over 12, and then I'm going to make another little spot here for B and H, okay? The base here, it says it's in the joist position. Now remember, we have the plank position is where it is flat and it's just like that. Okay, and then the joist position is where you get this, and it's the way that it's like this. So joist, plank, joist, plank. Okay, so this is in the joist position. So the larger value is going to be the height. Okay, so this one, so plank, the longer value is base, joist, the longer value is height. Okay, that's terrible writing. I'm sorry. All right, so for this one, the base is 1.5 inches and the height is 5.5 inches, okay? And then we're just going to plug that into this equation here, and I'm going to put it in my calculator. We're going to put 1.5 times 5.5 to the third. So I'm going to just do this x to the third. If you want to do it, you just do x to the y, and then you put 3. and then we're going to divide that whole thing by 12, and it gives us 20.79, or let's just say 20.8. Okay, so this basically becomes 20.8, and that's inches to the fourth, because it's inches times inches to the third is going to lead us to inches to the fourth. Okay, now we have all our values. Now we just plug it all in. So delta max equals F, which is 550 pounds, times L, which is 168 inches, to the third. So this whole thing goes to the third, divided by 48. 48. E, which is 5,400,000, times I, which is 20.8. Okay, so this is times, and this is times. We're going to put all this on the bottom in parentheses, because if it's in parentheses, then then it'll divide this whole thing rather than just the first number. So we take 550 times 168 to the third power, divided by, we'll put this all in parentheses, 48 times 5400000 times 20.8. Okay, and then when we divide those, we get 0.48. So it becomes a really small number, because it shouldn't bend a whole lot. Like, you've got something that's pretty strong, and you're putting 550 pounds in there, which is a lot, but it's only going to bend about a half an inch with that. Okay, so we'll get 0.48 inches is our delta max. Okay, all right. All right, we'll change the color here. We'll use the rainbow one. All right, so this says if a 92-inch beam that is 8 inches wide and 5 inches thick will fail if it bends more than 0.25 inches, if it's made of an aluminum alloy with a modulus of elasticity of 10 million psi, how much weight can it hold in pounds? Okay. All right, so this right here is our length. This right here will become our I. This right here is our delta max, and this right here is our E. So let's take all of those and put them as variables over here. So we've got delta max equals 0.25 inches. I'm really regretting this pen right now. F equals F, because we don't know what that's going to be. That's what we're looking for here, right? This how much weight, that's our F. L equals 92 inches. E is 10 million psi. And I is, well, we've got to find that, but that's going to end up being BH to the third over 12. Okay, I'm going to move this down a little bit. All right, and so that means base here. So we have wide and thick. Well, if we say something is 8 inches wide, that's going to be our base, and the thickness is going to be our height. Okay, so we're going to get 8 times 5 to the third over 12. So that's going to be what? 125 is 1,000 divided by 12. All right, so 8 times 5 to the third divided by 12 gives us 83.33. Okay, 83.33 inches to the fourth. Okay, now let's put all these numbers in. We get 0.25 equals F times L, which is 92 inches to the third, over 48 in parentheses times 10 million times 83.33. Okay. All right. Our variable is right here. Okay. We want this variable to be alone. So what we're going to do is we're going to rewrite this. We got 0.25 equals F times 92 inches to the third over 48 times 10 million times 83.33. Okay. The reason we're doing this f is just being multiplied by the 92, and then it's being divided by this. So we can just say f times 92 to the third divided by this. This will just make our calculations easier when we get to doing a little bit of algebra. So we'll bring up the calculator. So we get 92 to the third, excuse me, divided by 48 times 10 million times 83.33333. Okay. All right. And we get a very, very small number. That's okay. Okay. That's okay. 1.946 times 10 to the negative fifth. That's a very small number. All right. So we're going to take that number and we're going to bring it over to the other side. And since it's being multiplied by the f, we're going to divide by that answer. Okay, so we're just going to take 0.25 divided by that answer. So we're going to take 0.25 divided by, and we'll find our answer, which is right here. I'm just going to copy that. Oh, no, it doesn't let me do it. Crap. All right. We'll just say 1.95 times 10 to the negative fifth. 0.25 divided by 1.95 e negative 0.25 divided by, oh, we're going to redo this. Man, I got to edit this video. Maybe I could edit everything. I don't know. 0.25 divided by, what was it again? 1.95 e. We'll change this to a negative 5. 12,820. This stuff, 12,820 pounds. Okay. Now, this is aluminum. It's something that's supposed to be strong. So we've got a strong beam that's going to hold up and make sure that it's not going to be destroyed by lesser weights. Okay. All right. That's enough.